Back in chapter 2, I talked about this idea of a relation in light of sets. I talked about binary relation. A binary relation from A to B, I'll call it R, is really just a subset of the Cartesian product A cross B. All right, wait a minute. What's a Cartesian product of two sets? What's this thing? I know chapter 2 was a while ago, but we do still need it. What's a Cartesian product? Yes, but with a couple of specific restrictions. It's every combination possible of an element in the first set followed by an element in the second set. So these are things that look like ordered pairs. AB, where little a is in the set capital A, is one type, and little b is in the set capital B. Okay. So I'm going to pull two sets. Let's let capital A be the numbers 1, 2, 3, 4, and capital B be little a, little b, little c, little d. You'll notice these don't have to have anything in common. They don't have to even be from the same universe. I've got integers and I've got letters. But I can pick any subset you want from the Cartesian product here. As an example, here's a relation. One C, 2B, and 3C. Those are all valid ordered pairs within the Cartesian product. I just picked 3 of them at random. I could have anywhere from 0 to 16 items in my relation. Why do I know there could be 16 items in my relation? Because there's 4 in set. Multiplication principle, 4, 4. Perfect. I could have any of them that I want, as many of them or as few of them as possible. So anywhere from 0 to 16 in this case. If I want to think of this as a binary relation, I really want to think of it like an operator. I think of a binary relation as doing something to these two elements. So I would write that 1 is related to C, and that 2 is related to B, and that 3 is related to C, using this R like an operation. These things belong together. This is referred to as mid-fix notation because the operation's in the middle of the two elements. You can also do prefix and postfix notation. Prefix would put the relation in front. And postfix would put it afterwards. This textbook really only deals with mid-fix notation. There are valid places where prefix or postfix are more appropriate. Postfix notation is stack notation, all you computer science data structures people. If you haven't taken data structures yet, it's coming. I could do this visually as well. I could write the two lists, A and B, literally as lists. And then my relation R shows me that 1 is related to C, and 2 is related to B, and 3 is related to C. I could make an ordered pair chart. One is related to C, 2 is related to B, 3 is related to C. I suppose if I really want to do this, make it look professionalish, I should kind of make a grid here to pick from. Make sense? If I let my two sets be the set of cities in the United States and the set of states in the United States, then I can define a relation A is related to B if city A is in state B. And then I could write that, Greensburg is related to Pennsylvania, right? But Greensburg is also related to Kansas. Miami is related to Florida, but Miami is also related to Oklahoma, Arizona, Missouri, New Mexico, Texas, Iowa, Indiana, and West Virginia. I bet you didn't know there were Miamis in all of those. But that's okay. A relation just generally associates these things together. But in chapter 2, we were very specific. We talked about functions, right? A function is really a kind of a relation. What was it that made a function a function? Chapter 2, section 2 or 3? 3, I think. This is the same rule we came up with in algebra. We just had a visual interpretation for it in algebra. What made a function and not a relation? The vertical line test. And if I think of this in general set ideas, the vertical line test, that means each x only has at most one y. So in terms of the sets, each element in A is assigned to at most one element in B. There's my vertical line test. Clearly, Miami fails the vertical line test in our relationship about cities and states. Greensburg fails the vertical line test. Pittsburgh fails the vertical line test. There is a Pittsburgh, North Dakota. This is what you get when you get on Google and look at the United States. Now, we had all sorts of special other properties about function, one-to-one and onto, but this is the critical property, that I can only go from one thing to one thing. That is not true for a relation. Consider this definition for my relation. X is related to Y if Y squared equals X. Graphing time. Back to algebra class. Well, technically, I think this would be in pre-calculus, where you covered conic sections. Remember conic sections? Parabolas ever? What the hell is this as a conic section? There's a conics app on your calculator if you don't remember these. Do I hit the apps button? And if I tap on one of these, it'll show me the equation. Huh? Y squared equals number X squared. This is a parabola. And it's not just any parabola, it's a parabola that opens sideways. This is the parabola that opens to the right. It fails the vertical line test. 4 is related to 2. Yes? Because 2 squared is 4. But 4 is also related to -2, because -2 squared is 4. Normally, when we write a function that satisfies this, we write the square root function, yes? But if I write this, I've lost half of my relation, haven't I? I've chopped my relation in half. What do we normally do to fix that? Plus or minus. Which really makes it 2 separate functions, the top part and the bottom part. This is called a branch for a function. That's the last you'll hear me talk about branches. Branches were part of my PhD research. They're cool. But really, I want to think about relations more than I want to think about functions. I just wanted to let you know, you've done all this crap before. I'm just putting it in new language. You've seen all of this. Questions? If I think the plus or minus on the square root, there's one spot that's on both of those, right? The square root of 0 is 0. That's on both the top and the bottom. So that's called a branch point. I'm done. We talked about a relation from A to B. If I talk about a relation on a set, then I'm going from the set to itself. almost all of the relations I like studying in math tend to be of this style. The relations on a set. Example. Please notice that I define all of my relations using if and only if sentences. A is related to B if and only if A divides B. This is, again, the most appropriate way to use a definition is to think of it as an if and only if. I'm telling you, this is the term I want to call anything that satisfies these properties. So when you see this term, it means these properties. And when you see these properties, it means this term. That's the definition of an if and only if. Okay. I would like you to write the ordered pairs that are in this relation. How many ordered pairs do you have? You have 8. Does anybody else have 8? Anybody have nothing, something other than 8? Has anybody else finished writing down the ordered pairs in this relation? Come on, people, talk to me. A is related to B if A divides B. Who's got something other than 8? A bunch of you are looking at me like I just whacked you in the face with a fish. You have 5. Which 5? Okay, but you have this, right? So what's missing from here? Because every number will divide itself. So as soon as you gave me 1, 1, Gracie, I started thinking about, oh, I should include the number with itself. You could draw a diagram for this, right? You could write a list from 1 to 4. You could write another list from 1 to 4, and you could put arrows from 2, right? It is not a requirement that my sets be finite. The set Z is infinite. I can define a relation on the integers. A is related to B if A is less than or equal to B. Kind of difficult for me to write a diagram for this one, isn't it? But I could still visualize this. Because this is going to be the set of all ordered pairs, right? So what if I replace A and B with the letters X and Y? Well, then I could actually think of what's going on here as a graph on the set of dots that have integer coordinates in the xy plane, right? If I think of this infinite lattice of dots extending forever in the y direction, forever in the x direction, then I could graph by shading in or circling all the dots that are part of this. So I could say, oh, this dot is part of it, this dot is part of it, this dot is part of it. Because that's where the x and the y are equal, yes? Here, the y is 2, the y is 1, the x is 0, that one's in it. This one's in it, this one's in it. Oh, y bigger than or equal to x, isn't that everything up here? We graphed linear inequalities in algebra in chapter 9, a long time ago in a galaxy far, far away. Happy Star Wars Day, by the way. But I can clearly say these numbers are part of it, these numbers aren't, these ordered pairs are in, these ordered pairs are out. This is a well-defined set. Back to chapter 2. If A is a finite set, then there are how many elements in the Cartesian product? Exactly. It'd be cardinality of A squared. And then each one could be in or out, right? For each of these ordered pairs, I have a choice, in or out. So when I said there could be as many as 16 ordered pairs, when I only had the set that went from 1 to 4, that means there's 2 to the 16th possible different relations there. These choices get huge really quickly. Questions? Relations are sets. I can play all my set games, unions and intersections and things like that, right? Complements and all. I do all the ands and ors and nots all over again. Wow. So all of our set ideas come back here. I'm going to put these in new language. I want to know whether or not certain ordered pairs are in my set. I want to know if I have some ordered pairs, do I have others? And these are the properties I want to look at for a relation. A relation is reflexive if A is always related to A for every element in my set. We've seen an example of a relation that is reflexive. What example did I give you that is reflexive? I've given you two of them. Evan? The A divides B one, right? A always divides itself. 0 is no zeros with 0 left over. And A less than or equal to B is reflexive. Because A is less than or equal to A. Oop, there we go. If it's equal to, it's definitely less than or equal to. But if I replaced this with strictly less than, it would fail to be reflexive. Quite often, we can think of this idea as a property, right? Divisibility is a property of numbers. Every number divides itself. That's what it means to be reflexive here. But I can do this on me. Questions? Now we start getting into cases, if I have some relations, some ordered pairs, do I get others? So R is symmetric. If I have the ordered pair AB, I also have the ordered pair BA. Are any of these previous examples symmetric? If I know that A divides B, do I automatically get that B divides A? Let's go back and look at the example we did. We had 1 divides 3, but 3 doesn't divide 1, does it? Okay. So unfortunately, no, this is not symmetric. Is less than or equal to symmetric. If A is less than or equal to B, does that automatically mean that B is less than or equal to A? No, not at all, right? Same thing with less than. If A is none of those that are up there happen to be symmetric. So what could be an example of a symmetric relation? Here's one. What? If I know that A is equal to plus or minus B, how do I know if I switch the two order and get B equals plus or minus A? Colin? The only thing that can change is the plus or minus, so I think of it as like the absolute value. They have the same absolute value, it's whether or not they have a different sign. Evan? They're the same distance from zero. But I can actually do it by cases. Here's a proof. If A is equal to B, well then clearly B is equal to A, right? If A is equal to negative B, then B is equal to negative A. And these two together mean A is equal to plus or minus B. And these two together mean B is equal to plus or minus A. I really just have to move the plus or minus from one side to the other, don't I? Symmetry of a relation is a useful idea. But as we've seen, some of the nice relations that are reflexive turn out not to be symmetric. But this next one is weird. Now you might think R is anti-symmetric means that it's not symmetric. I wish that were the case, because that would just be easier, but it's not. This is a new definition. Let's suppose that both AB and BA are in my things. Those would be the pieces that made up symmetry, right? The only way to have that happen is if the two things are equal. Now, this sounds really tough. The only way I can have both A and B and BA in the relation is when the two numbers are the same. Here's an example. This is the relationship R. A is less than or equal to B. If I tell you that A is less than or equal to B and B is less than or equal to A, what's the only way that works? They've got to be exactly the same spot, right? I've got two spots on the number line. A is to the left of B, or it's on it. B is to the left of A, or it's on it. The only way that's going to both work at the same time is if they're exactly in the same spot. If I only think of positive numbers, then it turns out that divisibility is anti-symmetric. Okay, wait a minute. What the fuck? Okay, if A divides B, what does that mean? Chapter 4, Section 1, divisibility. With zero remainder. That means that B can be written as number times A plus 0. I'm just going to write that as K1 times A. But if B divides A, what does that mean? Here, wait a minute. A is equal to K2B, but B is equal to K1A. Put those together and I get A is equal to K2 times K1 times A. What's that tell me about K2 times K1? Oh, wait, there's more. It's not just any integer. It's 1. And K1 and K2 are integers. And the only two integers that multiply together to give you 1 are? The other possibility would be -1 and -1, right? But I said that A and B were both positive. And that means that A equals B. If you have two positive numbers that divide each other, the only way they can do that is to be the same number. Anti-symmetry is weird. I would have hoped it just meant not symmetric, but no. Stupid relation authors. I don't tend to use that one as often I use the other two, which is why I don't have a lot of examples of it. It doesn't come up as frequently. There are a number of cases specifically in electrical engineering because of circuit paths and voltages and things like that. But otherwise, it's a rare thing in my opinion. One more property. I've seen this word before. Where have I seen this word before? All the way back in chapter 1. What did we call transitive back in chapter 1? This should be on your formula sheet for exam 1. It had a different name and we called it transitive because that was easier to remember. our hypothetical syllogism. Back in our rules of inference, chapter 1, section 6, I think, the hypothetical syllogism says, if P then Q and if Q then R means if P then R. In this language, I'm going to say, if I have AB and BC, then I got to get AC. Divisibility works here. If A divides B and B divides C, then A divides B means B can be written as some number of A's. B divides C means C can be written as some number of B's. Change the B to some number times A. Oh, I get N1 times N2 times A. Less than or equal to is transitive. If A is smaller than or equal to B and B is smaller than or equal to C, then A must be smaller than or equal to C. I don't have to have less than or equal to. I can just do strictly less than here, right? Equals is transitive. If A equals B and B equals C, then A must be equal to C. I like this one. Frequently, we do unions, intersections, and differences. For example, here are four relations where A and B are elements of the integers. I can think of adding as the union of two sets. R1, sorry, R2. Wait a minute, I wrote the same thing down twice. That should be an equal sign. R2 union R3 is R1. R2 is the less than, R3 is the equals, R1 is less than or equal. What is the intersection of R3 and R4? Hang on a second. R3 is equals. R4 is not equals if I take what's common to both of those. What ordered pairs have A equal to B and at the same time have A not equal to B? None. An empty set. If I do set differences, R1 minus R2 gives me less than or equal to, take away the less than part, gives me the equal part. Questions? It's a headspace switch. I think of this like a function. I think of it as taking one object and giving me another one. I think of this as a set. I think of it as putting two ordered pairs together. I want to be able to switch back and forth between the two perspectives fairly easily. Because if I think of functions, I can think of a relation from one set to another, right? R from A to B. These were relations on a set. They were from A to A. But we didn't start that way, right? We started with cities and states. The set 1, 2, 3, 4, the set A, B, C, D. There's no requirement that it's the same thing. But let's suppose I have this and I have another relation from B to C. Well, then I could define the composition as taking something from A and spitting out something in C. But how are we going to do this? Oh, we're going to do R of A, and then we're going to do S of that. That's even how we read that little circle in calculus. Remember the chain rule? F of G of X, S of R of A, S of R. An example. Human beings. I'm going to be a little pedantic here. In my set of people, A is related to B if A is a parent of B, and I mean biological parent, a contributor of genetic material. We can talk about adoptive families all you want, separate issue. We go with biology here for the moment. Huh. What does a composition mean here? What does it mean to do R of R? A is related to B means A is a parent of B. So R of R would be A to B and B to something else, right? B to C. What is A to C? Say again? A grandparent. I can define as far as you want, right? This is R squared. I could do R cubed and get great grandparents. I could do R to the fourth and get great great grandparents. How far back do you want to know your family tree? This is what Ancestry.com is about, right? Powers of R. I can think of this whole collection. R of R, R of R of R, and so on, right? R is transitive If and only if that set is contained within itself. That's going to be something that's going to be hard to figure out. That's not an easy thing to figure out. I got to look at infinite collections of sets. I need a better way. That better way will come to us on Wednesday. I will see you all then. I hope you have a wonderful rest of your day.